Hey everyone, so today I'm going to be explaining the Chatelier's principle because yesterday we were learning about chemical equilibrium when the forward and the reverse reactions in a chemical equation are going to be occurring at the same rate, and that equilibrium is going to make it look like your amount of products and reactants are staying consistent even though the reaction is still occurring. Oops. There we go. So if the system is disrupted in any way, this is when Le Chatelier's principle is going to take into effect. So if you disrupt your chemical equilibrium, then it's going to try and shift to try and restore that equilibrium. And so that's what we call Le Chatelier's principle. And there are three stressors that can affect this equilibrium that a chemical reaction has. The first is going to be changes in concentration. So that's really just the amount of your chemicals that you have. That could be the amount of reactants or the amount of products. The second is changes in pressure. That's going to be for gases only. And your third is going to be changes in temperature. So what's going to happen if you have a change in the concentration? If we've got this equation here, A plus B is reacting to form the products C and D. So if we increase the amount of reactants, A or B or both, then our whole equation is going to shift to the right to try and balance out that increase in the reactants. So then we're going to try and produce more products, C and D, to try and balance out that equilibrium again. The opposite is also true if you increase the amount of products that you have, like if you introduced more of C or D, then your reaction is going to shift back to the left and it's going to try and balance out by creating more of the reactants. So it's going to shift to the left. The same is true if you were to take things away. So if you were to take the amount of reactants away, A and B, then your whole thing would shift to the left to try and increase those amount of reactants again. And the same thing is true on the other side. If you were to take away C and T, then your whole equation is going to kind of shift to the right to try and produce more of those products again. You can kind of think of this like a little seesaw. And so if things are in equilibrium, then your products and your reactants are balanced, even if they're not exactly equal amounts. But then if you take away, let's say if you take away some of your reactants, so that side goes down, then we're going to try and make more of the reactants and shift it back to equilibrium. Okay, so it's kind of like a little seesaw effect there. All right, our next one is going to be changes in pressure. So this is another stressor or disruption into our system, and this is going to occur for gases only. So if we're looking at this equation here, now we've added some coefficients into our equation. So we've got A plus 2B is going to form C plus D. And when we're looking at changes in pressure, we're going to look at the total amount of molecules or moles on each side of our equation. And you can think about changes in pressure having to do with changes in volume. So if you think about Boyle's law, which we learned about when we talked about gas laws, Boyle's law says that if you increase the pressure on a system, then you're decreasing the volume. Those two are related to each other in that inverse way. So you're increasing the pressure, you're squeezing something in, you're decreasing the volume. So it's helpful to think about this one in terms of volume. So if you increase the pressure and decrease the volume, your whole equation, according to Le Chatelier's principle, is going to shift to the side with fewer moles because you can't fit as many in anymore because you're decreasing that volume. So if we increase the pressure, we're going to shift to the side of the equation that has fewer total moles on it. If we decrease the pressure, we're increasing the volume, and so we can actually fit more moles in there. And so our equilibrium is kind of going to shift towards the side with more moles. You can think about this like if you wanted to go out to eat, and let's say you really wanted to go to a pretty small restaurant because they had really good food. If there's a fairly small restaurant, you're increasing the pressure and decreasing the volume because there's not a lot of space inside that restaurant. And so you know that you can only bring like maybe one other person. So you're going to only be able to fit a few people in there. You can't bring all of your friends. Versus if you wanted to eat out and you were going to go to like a really large restaurant, then you're increasing the volume of your space and you can fit more people now. So then your kind of equilibrium in this situation is going to shift so that you can invite a ton of people. So that's kind of how this is going to affect the amount of moles that you have. So in terms of this equation, you're going to use the coefficients to determine the amount of moles that you have on each side. So on our left side of this, of our reactants, we've got A plus 2B. So we've got 1A and 2B. So we've got 3 moles on our reactant side of things. On the other side, on the product side, we've got 1C and 1D. and so we've only got 2 moles on that product side of things. So we know that looking at this, we have more total moles on our reactant side, on our left side of things. So if we were to increase the pressure and decrease the volume, we're going to have to switch to the side with fewer moles. So we're going to make more products. If we were to decrease the pressure and make things a little bit more spaced out, then we can shift to the side that has more moles on it. So then we would make more of our reactants. And we'll do an example with all of this stuff at the end. All right, so our next one is going to be changes in temperature. So to determine what's going to happen with changes in temperature and which side we're going to kind of shift to in our equation, we're going to figure out whether or not our reaction is endothermic or exothermic. So we're going to kind of add energy into this reaction. So on our reaction up top, we can see that this time we've got A plus B is forming C plus D, and that we're sending energy out, we're releasing energy. So this is going to be an exothermic reaction because energy is exiting this system. And so we're forming energy, we're forming heat, and so that's going to be an exothermic reaction. That means that the opposite reaction, in a reversible reaction, going back the other way, is going to be endothermic. Because if we're going back and shifting towards our reactants, then we're using energy in there. So if we were to add temperature into this system, or increase the temperature, it's a better way of saying it. If we were to increase the temperature in this system, we don't want to continue to make products, because that's going to continue to increase the temperature even more, because this is an exothermic reaction and we're forming energy from this. So what we really want to do if we increase the temperature here is actually shift back and use some of that energy to do the reverse reaction and start to form some of the reactants. So that's going to shift this entire thing to the left. If we were to decrease the temperature of this whole system, then we're going to try and replenish that by continuing to go in the forward direction and form some of the products, because energy and heat is one of our products. And the opposite is going to be true for an endothermic reaction. So again, we'll do some examples later. So these are just some reminders about endothermic reactions and exothermic reactions. In an endothermic reaction, energy is entering the system. So our temperature is going to decrease because we're putting energy into the system, and so overall the temperature is going to go down. And we can consider heat to be a reactant, so we can actually consider it to be on the left side of this because it's entering into the system. Versus an exothermic reaction, heat is exiting, so our temperature is going to increase. We're going to be able to feel that heat that's exiting, and heat can actually be considered a product in an exothermic reaction. All right, so let's do some examples. So in this particular example, we've got a concentration change. Sorry, I'm trying to move my little video so that you can see it fully. So for a concentration change, remember we're just talking kind of about the amounts of our different products and reactants. And the G in here in the little parentheses just means that these things are gases. So that's just looking at phases, so we don't need to worry about that. So in this particular concentration, we've got A plus B, and we've got 2 moles of A and 3 moles of B is forming 2 moles of C and 1 mole of D. So now we're just really talking about increasing or decreasing the amount of our products and reactants. The brackets down here in the action section, that just means concentration. That's how we abbreviate concentration, is in brackets. So if we were to increase the amount of our reactants, A or B, on the left side of things, then our effect is going to be that we're shifting to make more products because we've increased the amount of reactants that we have, and so we're going to try and use some of those up. If we were to increase the amount of products that we have, we're going to try and use those up by shifting back towards our reactants. So then we're going to shift towards the left. Likewise, if we were to decrease our amount of reactants, A and B, we've taken away some of those, and so now we're going to try and make more. Our system is going to shift actually back towards our reactants because we've taken some of them away, and so it's going to try and make more of those reactants. If we were to take away some of our products, the system is going to say, hey, we need to make more products to replenish those, and so it's going to shift back towards the right, towards the products. So that's how concentration is going to affect this. For a pressure change, remember we're kind of relating pressure to volume. So we're either squeezing things and increasing the pressure, and so decreasing the volume, or we're decreasing the pressure and making things a little bit more spaced out. And so for this, we really have to count the number of moles that we have on each side of our reaction. And to do that, we're going to look at our coefficients. So for our reactants on this side, we've got 2 moles of A and 3 moles of B. So overall, we've got 5 moles total on our left side of our equation. On our right side for our products, we've got 2 moles of C and 1 mole of D, so that's going to be 3. So we've got more total moles on our reactant side than our product side. So if we were to increase the pressure, we're decreasing the volume, so we don't have as much space anymore. So we're going to shift towards the side with fewer total moles because we don't have as much space to fit things. So we're going to shift and we're going to make more of our products in this particular case. If we were to decrease the pressure, we have more space. So we're going to shift towards a side that has actually more moles because they can actually fit in that space now because we've decreased the pressure. For temperature change, we're going to look at 2 different ones. We've got endothermic for this one. So in this particular example, we've got A plus B plus heat because we're putting heat into the system. So remember, you can think of heat as an actual reactant in an endothermic reaction. And then we're using that heat and those reactants to form C plus D. If we were to put heat into this system by increasing the temperature, we can basically think of this as a reactant. So we're increasing our reactants, and that means that we're going to try and make more products to use up some of that heat. And the opposite is true. If we were to decrease the temperature, we're basically taking away one of our reactants. And so we're going to shift towards our reactants to try and make more of that heat. So really, you can think of heat as almost being like the reactants and products. And if you ever are like increasing the amount of something, then your system is going to shift away from that because it wants to use up what you've increased. And if you ever take something away or decrease an amount of something, then the system's going to shift towards whatever you took away to try and replenish that thing that you took away. So that's going to be true for both concentration of things and for heat. So that's how you can remember that. And for an exothermic reaction, so same equation here, but in this case, we're actually producing heat. So this is an exothermic reaction. If we were to increase the temperature overall, remember we're shifting away from that thing that we're increasing. And so we're going to shift towards the left away from the heat because we've added some. If we were to take away heat by decreasing the temperature, remember when we take something away, we're going to shift the whole thing towards that thing we took away so that we can replenish it. So then we would actually shift towards the right. So we're going to work on this tomorrow also, but I'd really like you to complete the Google form today. Today is Wednesday, so hopefully get that done today so that I can see if there's anything in particular we need to work on for tomorrow.